Good late afternoon. So I'll be talking a bit about both what my company is doing in RISC-V in terms of specification work and enablement, as well as in the ongoing efforts at RISC-V to address the AI, ML, and the high-performance computing market through new standards that we're setting through the RISC-V international processes. So RISC-V is unique because it is really upending the economics of custom silicon today. So there's a number of things that make it fit perfectly for accelerators, for integrated solutions, or any kind of device that needs acceleration or has domain-specific workloads. So it has industry-leading differentiation because it is open to add any kind of domain-specific acceleration, custom instructions, and any kind of addition that you wouldn't be finding in another ecosystem. So if you look at x86, for example, your freedom is limited to choosing one of two vendors that you can buy a chip from. If you're looking at ARM, your freedom is limited to licensing a core or to licensing the ISA and implementing it exactly the way that it is defined. But RISC-V allows you to add and remove instructions just as you see fit and build up an integrated solution that fits your specific market and fits your specific applications. So that is just part of the RISC-V solution and part of the unique selling points that RISC-V is offering. The second part, and that's critical to new adopters, is that we are having one unified ecosystem that is supporting this. So you've heard before about various of the software stacks. You've heard about how we're bringing applications to RISC-V. And that is not just limited to the automotive market, to Linux. This is actually limited, this is actually extended to all of the software. So it starts with having one tool chain, having these tool chains fully upstream, enabling things in the open source, and having the flexibility in there to address various versions of RISC-V with different extensions, but just recompiling. So this flexibility that we have to customize is actually giving us an industry-leading differentiation. So every core can be tailored. It's not just additional custom extensions. It's microarchitectural evolution. It is improvements to those open source tools that allow you to take advantage of whatever you do in the chip, the freedom to add specific software that is tailored to your chip, and of course, an attempt at the RISC-V level to reconcile that through profiles. So we're building up these profiles which give you a defined base that you can add innovations and accelerations on top. The second important part to this, just as I outlined before, is that we're creating these choices as interoperable choices. So if you have the RISC-V instruction set, if you're targeting with your software, that software can move between chips from different vendors. So it isn't a lock-in despite offering the differentiation. And if the software stack is built right, you get acceleration on one device, you move it to another one, and you're picking up the acceleration benefits of that device automatically as well. And finally, RISC-V is being adapted to applications today. It is being adapted by various member companies. You've heard them before. And we are still adapting it on a specification level. So us as consultants, us as researchers, us as engineers, we're adding new instructions today by analyzing the workloads, emerging workloads like AI, emerging new algorithms in order to build the best cores possible and to help semiconductor companies to build the best cores possible, and taking these innovations and putting them into a standardization process so that we actually end up with interoperable solutions again, despite having a continuous drive to improve what we have. So that has actually led to some interesting news over the last year. RISC-V has become the de facto architecture for new AI accelerators. We're seeing a number of adoptions based on these basic tenets of the freedom to innovate and the adaptability to new applications and this adaptability to new algorithms. So Meta has announced that their tensor accelerator, that their AI accelerator, which is in-house developed, is based on a RISC-V core, of course, and adding their own secret sauce as an accelerator block. Google has done something similar. They picked up RISC-V based on the Sci-5 core, together with their acceleration engines, to build their next generation tensor unit. And those are all pre-standard solutions. And most excitingly to me, because they're good friends, they are partners of ours, Stream Computing here in Beijing has developed a complete AI accelerator solution built on RISC-V, completely open in terms of reusing the RISC-V the RISC-V instruction set, the RISC-V basic software, and adding matrix extensions on top of that, and even open sourcing the specification of it. In addition to that, we're having quite a number of other adopters out there, like Esperanto, Revos, SoftGo is a big adopter of RISC-V and also well known in the AI market. Ventana has publicly released that they will be using RISC-V to drive AI in the data center. And all of this is pre-standards. And why am I saying pre-standards? These have been companies that have been adding their own solutions based on the standard, that have been adding custom instructions, but haven't really had the luxury of building that on one uniform standard. So as RISC-V is upending the economics of AI accelerators by providing a common base instruction set, having that freedom to add custom instructions, and yet providing a shared instruction set, we're aiming to standardize these instructions as far as we can so that we provide even more benefits. So today, you're getting 80% out of the RISC-V based specifications, and you're adding 20% yourself if you build an AI accelerator. But in a year, in 2 years' time, you will be able to pick up 98% out of the standard specifications, out of the shared common good, and you will have to add only 2, 3, 4, 5%, which means your own microarchitecture, a few DSAs in order to be competitive, while being able to pick up almost everything that you need, just out of the shared knowledge and out of the standards. So how can we do that? Why is RISC-V so popular with AI ML? And the answer to that is quite simple. AI is basically software defined. You're working your way down from the algorithms. You're working your way down from the applications to understand what your hardware needs to do. And RISC-V is, as I said before, customizable. It was designed with customization in mind. So it is very well fit to customize it to those applications. And AI, on the other hand, is rapidly evolving. So if you don't have that freedom to optimize, if you don't have that freedom to customize, you may miss the optimization opportunities. And keep in mind, transformers, the original paper that was introducing transformers, which are used in large language models today, was only published in 2017. So we're talking about AI moving so fast that 7 years ago, the model, or the most important model for commercial exploitation today, wasn't even published in literature yet. So I was mentioning before that RISC-V is trying to standardize as much of the instructions that you need for the optimization and for the implementation of AI and HPC today. And that is so RISC-V can become a common language for AI. So today you're having plenty of closed platforms, plenty of closed solutions. If you look at NVIDIA, they have their own proprietary stack. Some of the specifications are open, but they're all owned by them. And they have restrictions on what you can do on other hardware with it. RISC-V is trying to address this by specifying its own optimized instruction sets for AI. Part of it is the integrated matrix extension, The other one is the attached matrix extension. And you may ask, why two different standards? Have these people lost their mind? The reason for that is that we are trying to provide choice. So again, we're coming from a point where you want to customize, where you want to tailor, but we're at the same time trying to standardize. So one of the solutions is trying to build up from vectors. Give you a good speed up. Target the middle of the market. Automated driving, image processing. The sort of applications that are well known. And then get another solution that will scale much higher, that will be able to address the HPC part, that will be uniquely suited to AI ML, and that will add its own set of microarchitectural resources, and that's the attached matrix unit. So imagine that as an accelerator on the chip. And using this approach, we have the ability to actually address all market segments. So matrix on RISC-V is not just going to go after the high end. It's not just PCs, data center. Matrix will be useful on DSPs, embedded solutions, cameras, and then you take it up a notch to your PCs, to the data center, and of course into cars. And for every one of those solutions, based on these two standards, you will be able to pick the right solution, the right microarchitecture, the right architecture underneath it, and decide how much silicon area you will devote to it. And there is nothing that forces you down one path or the other. These are architectural specifications, so you can have both of them implemented on the same chip. You can have both of them implemented on the same chip and share microarchitectural resources, basically the same silicon area, and map one onto the other. And that's not just enough. If we are looking at AME, at the attached matrix extension, we're actually looking forward today already towards tensors. So not just matrix, higher dimension operations, tensors for AI, for machine learning. And of course, all of that still backed by unified enablement. So having one set of intrinsics, one set of libraries that is going to map down to both of the IME and the AME extension. So you write your software, it calls the intrinsics, and depending on what your chip provides, you will get the optimal performance. And as we're talking about this, we're actually also looking forward at the future. So today we are addressing matrix. Next step is going to be tensor. However, there is one big convergence going to happen. GPU workloads, GPU workloads. All of that is meant to be unified on just one heart. You have CPU, you have GPU, you have GPU workloads. So the CPUs are evolving towards more throughput. Basically where GPUs and GPUs have been in the past. We have vectors, wider vectors, many core. And on the other hand, the GPU is evolving towards more flexible programming. So in Shreyas' presentation just before, he was pointing at the fact that the GPUs that Imagination is shipping are adding more flexibility as needed to address new algorithms. And as we're going down that road, in a few years, you're going to see RISC-V evolving, not just towards matrix tensor, but also adding hardware multithreading and graphics instructions so that we can do everything on a single resource. And this is where we are coming in. This is where VRULL is coming in, because we're today a leading force to drive programmer productivity through unified compute in RISC-V. We're adding the software and toolchain support. We're working with a number of semiconductor companies to define the necessary APIs for compute and acceleration, to explore the workloads, provide the intelligence that you will need, the benchmark know-how that you will need in order to decide on the optimal instruction set and the optimal DSA extensions, as well as the optimal microarchitecture. And finally, we have been active in the ecosystem for the last couple of years and have contributed to a number of standards. So if you are defining your instructions today, you can work with us to actually lift them up to the level of a standard by using our know-how and our experience to get this codified in a way as in RISC-V, to get it fully tested and move it through the international standardization process. That's going to help you to make your specification better and also well recognized and ratified. Thank you for your attention.